When trying to prove the statement P implies Q, it can sometimes be hard, or even impossible, to prove it in full generality. It is very useful to break down P into a number of cases P1 up to Pn, where P is just P1 and P2 and all the way to Pn, because all of these cases must be true in order that P is true. Then, we try to prove that Pi implies Q for every I from 1 to n, which is very often easier than proving all cases at the same time. Let's consider this example. A times B equals 0 implies A equals 0 or B equals 0. In other words, if A times B is 0, then we want to show that A equals 0 or B equals 0. We can break it down into two cases. Either A equals 0 or A is not equal to 0. For the first case, A equals 0 is one possibility of the result that we want, so we don't have to prove anything. For the second case, since A is non-zero, we know that 1 over A exists. Then, we can multiply 1 over A to both sides of A times B equals 0 to get 1 over A times AB equals 1 over A times 0. The right-hand side is just 0, and the left-hand side simplifies to B. So B equals 0, which is the other possibility of the result that we want. Hence, the result holds in either case, and the proof is complete. Let's consider another example. If n is an integer, we want to show that n squared plus 5n plus 2 is even. Since we want to show that some number is even, it helps to divide the assumption into the cases where n is even and n is odd. First, consider when n is even. Then, we can write n as 2k for some integer k. So we can substitute this expression into n squared plus 5n plus 2 to get 2k squared plus 5 times 2k plus 2, which equals 4k squared plus 10k plus 2. Since we want to show that the number is even, we try to take out a factor of 2 in the expression. So we have 2 times 2k squared plus 5k plus 1. This shows that n squared plus 5n plus 2 is even. Now consider the case when n is odd. This time, we can write n as 2k plus 1 for some integer k. So let's substitute this expression into n squared plus 5n plus 2 to get 2k plus 1 squared plus 5 times 2k plus 1 plus 2, which equals 4k squared plus 4k plus 1 plus 10k plus 5k plus 2, which equals 4k squared plus 14k plus 8. Again, we take out a common factor 2 to get 2 times 2k squared plus 7k plus 4. So n squared plus 5n plus 2 is again even. We have shown that n squared plus 5n plus 2 is even no matter n is even or odd, so it is even whenever n is an integer. Let's look at a harder example. This time, we want to show that if n is an integer, then we always have n cubed minus n equals 3k for some integer k. Let's think about this. Should we separate into the even and odd cases, like in the previous example? Not really, because we are not trying to prove that a number is even or odd. So what are we trying to prove? We are trying to prove that n cubed minus n is 3 times an integer, or in other words, n cubed minus n is divisible by 3. So we are in the realm of divisibility by 3 here. What are the different cases here? Well, if we divide n by 3, only 3 things can happen. It could be that n is divisible by 3, or the remainder is 0, which is the result that we want, or there is a remainder of 1. In other words, n can be written as 3m plus 1 for some integer m. The last case, of course, is the remainder is 2, so n is of the form 3m plus 2. Now, let's try to prove the result in each case. If n equals 3m, then we substitute into n cubed minus n, to get 3m cubed minus 3m, which equals 27m cubed minus 3n. We can take out a common factor of 3 to get 3 times 9m squared minus m. So one case is done. Next, n equals 3m plus 1. We substitute again to get 3m plus 1 cubed minus 3m plus 1, which is a bit clumsy since we need to expand a third power. We can use the binomial theorem or expand bracket by bracket to get 27m cubed plus 27m squared plus 9m plus 1 minus 3m minus 1, which equals 27m cubed plus 27m squared plus 6m. Again, we are able to take out a common factor of 3 to have 3 times 9m cubed plus 9m squared plus 2m. The last case is very similar. Upon expanding the brackets, we get 27m cubed plus 54m squared plus 18m plus 8 minus 3m minus 2, which equals 27m cubed plus 54m squared plus 15m plus 6, which equals 3 times 9m cubed plus 18m squared plus 5m plus 2. Again, a multiple of 3 as expected. So in any of the cases, n cubed minus n is 3k for some integer k.